Great. So last time we had spoken about the basics of dimensions. We had talked about the nature of a dimension, some of the reasons that they are valuable. And I distinguished between dimensions, which characterize sort of the type of quantity you're dealing with, the semantic category you're dealing with, length, time, person, coin flips, pressure, volume. Volume will be given by cube. So dimensions describe sort of the broad area in which your quantity is derived. Units describe the particular meter stick you're using to describe that, how you measure it, right? But what you view as one describes your point of view. What does one mean? That's what is it 1 month, 1 day, 1 year, 1 foot, one meter? That's what units characterize. It's a sort of how to measure it, right? And you can have many units within a given dimension. We talked about that, right? Seconds, weeks, days, eons, centuries, etc. for time. And we can convert between them with dimensional constants. Okay, we had spoken, given reference to the fact that dimensional systems are human creations, or things we create, but there are some fundamental things about the nature of the world that are independent of the particular unit system that we speak about. But to really motivate that and talk about it, I introduced the fact that when we have a quantity, a given value of some sort, we could think of the dimensions as being a product of powers of particular dimensions. So we have person per time, it's p to the 1 power t to the minus 1, because it's per time. Time is in the denominator, right? Or if you will, it's person times 1 over time. It will be equally well, good way to put it. So it's p to the 1, t to the minus. But what I'm leaving out is if we have a dimensional system which has some other dimensions like length and money, really the others have exponent 0. It's these exponents that are in this D. This real is just referring to the fact these numbers in the exponent in general are real numbers, like they're quantities that can be greater than 0, less than 0. They don't have to be integers. There are quantities called fractals that have fractional dimension. And sometimes you'll get things like, with a pendulum problem, you'll get things like the square root of 2, for example, as an exponent. But in general, we can write down the dimension for something as a product of powers of it. So this is a product of powers, even though we write a person over time, person times 1 over time, person times time to the minus 1. And I went through a bunch of examples on this last time. Is this notion clear to you? Like, is this notion of being able to write down a dimension for a given value? Is that something that you feel pretty comfortable about? Okay. Okay. But what I talked about, moreover, within a given dimension, we might have different units. Right. So we might be dealing with variously with length being measured in meters or in feet, for example. And we may need to convert between them. And the exponent associated with the dimension associated with the quantity. So if we have $1 per linear foot, right, for a quantity, I had noted that the multiplication we need to make to convert that to something measured in meters, dollars per meter, relates directly to this exponent. The fact that this is dollar to the one times foot to the -1 means that there's this multiplier of 3.2, in other words, number of feet per meter. Here. By contrast, if we're dealing with a quantity that's like dollars per square foot, like you're calculating the monthly rent for, for office space or something, or how much it costs to have tile laid in your house, number of dollars per square foot, tile laid. The fact that it's an exponent of 2 means that the dimensional conversion constant here is not just multiplying $1 per square foot times 3.02 feet per meter to convert that to meters. No, to convert it to meters, you need that factor squared. Because you have meters in one direction of length and meters in another direction of length, and it's the square of. So we need to, if we have a certain number of dollars per square foot, monthly rent, maybe it's, $5 per square foot in monthly rent. If you need to convert that to dollars per meter squared, now you want to consider how big that thing is in meters. You're going to need to multiply it by a factor of over 10, right? On factor of 3.2. Are people comfortable with that idea? And the point is, the fact that it's this squared comes from the fact this is dollars per foot squared. That's what dictates this conversion function. If it's 1 power, it's this ratio of 1 to the 2, or it's squared, it's this ratio squared. And if it's to the 0 power, if it doesn't depend on this, then it's whatever the ratio is to the 0 power, which is what? What's anything to the 0 power? 1. Yeah. Right. So any non-zero value to the 0 power, even 0 to the 0 power from listen. In any case, it would be 1. In which case, it would be independent of what unit you measure, in what measure you measure length. If you have a quantity which has a 0 power for length, then it means it's independent. The value of it is independent of how you measure length. Whether you measure length in foot or measure length in meter, it's going to be independent of it if it's a 0 power, right? If we have something. Remember, just a moment ago, we had like this incidence, 20 people per day are getting sick, person per unit time, or people per month that are getting sick, whatever it is. This has a power length to the 0. What that means is if I change how I measure length from meters to feet, I don't, or vice versa, I don't have to change this quantity. This quantity would be invariant. It doesn't depend on that. Does that make sense? Can you repeat that? Yes. What I'm saying is, when we have a quantity, I had noted that we can write down the dimension of that quantity as a product of powers, power meaning this exponent, of different particular dimensions. So if I'm talking about cash flow, for example, this would be dollar to the 1 power, it's up here in the numerator, divided by time. So it's, in other words, times 1 over time. So time to the -1, because it's in the denominator. It's like this over that, right? Incidence, number of people getting sick per month, for example, like a person divided by time, person to the 1 power t to -1. Are we okay with that? And what I'm saying is, you'll notice that each of these is not mentioning certain dimensions. For example, this one, incidence, doesn't mention anything about length, nor does it mention anything about dollar per unit time, right? You see that? Cash flow doesn't mention anything about people. It doesn't mention anything about length, right? But it says zero power. Right? Does that make sense? It's something to the zero power. Certainly any non-zero thing to the zero power is going to be one. So these are to the zero power. And what I'm saying is that's an indication it doesn't depend on any dimension that's to the zero power. A value characterized like this is going to be independent of it. So if I have some amount of cash flow, if I'm spending $500 a month, that does not depend on length, how I measure length. That does not depend on how I measure length, because its length is zero. It's independent of length, let's say, right? Now, this was leading up to a profound fact, which is there are certain quantities in the world where all of we express their dimensions as a product of powers. It's all with power zero, all with exponent zero. In other words, if we have a unit system of, let's put some colored chalk down here, and I have a bag of tricks. So I am going to pull that out and engage in rambunctious use of chalk. So if I have a dimension system which has a dimension dollars, a dimension time, a dimension people, and a dimension length. So any quantity has some dimension given by this to some power, this to some power, this to some power, that to some power. Like, tell me, how would I encode if I had a value that was dollar per person, what would I put here? If I wanted something that was dollar per person. So like how much it costs to get admission to, you know, to a flight, how much it costs to buy a flight ticket. It's a certain amount per person. What would the dimension be? How would I write that? Yes, is it in Alex?
Alex.
Yes.
Dollar to the one, T to the zero, P to the one, and L to the zero.
Okay, dollar. Okay, so L to the zero.
And then P to the one.
P to the one. It's all
negative one. Sorry.
Minus. Yeah, minus. Good. Good. Okay, what if I was considering the cost that each cost associated with getting YouTube Premium, and I want to consider it as a per person cost. So monthly cost for getting YouTube Premium per person, subscription cost. What would this be? Okay, so dollar, it's dollars, right? This is for the one. I'll put it that way. How about this time default? So it's a monthly cost. So per unit time, right? Per person also, right? The per person cost. YouTube Premium. I'm ignoring the fact that they have some family. Okay, yeah. Anyway. So this would be dollars per person per unit time. You can think of this as like person months, dollars per person month. How much does it cost to subscribe to YouTube? Alternatively, if you want, you can think of it as dollars per person. And you pay that amount per person per month, right? Or you could think of it, if you want, you could think of it as dollars per month per person. Right? All of those come down to dollars per person per unit of time, and if you write that out, it's dollars to the 1 times the -1 person to -1 length to 0. Are we comfortable with this? Okay, so how if we wanted to capture the amount of time it takes for a physician to see each patient? What would the units, what would the dimensions of that be? The time to see. For the dimensions, yes, Christina.
0, 1, 5,
0, because it's not something we're quantifying that you sort of dollar dependent. 1 for time, that's time per person. Time per person is what? Person. Oh, okay, yeah, okay, so, good point, I'm excluding doctors from my analysis per person. So it's -1, time per person they're seeing. You can think of it as like time per person, the grocery, okay, yeah, and, yeah, time per person, we're not gonna consider the doctor, that's an interesting point, think about, the few people involved, okay, so this would be time per person, right? For them to receive care, right? Time per person, are we good with this? Are people feeling comfortable? Okay, now. What would it mean? I need to. Go over and. Give some equity to this side. So these are my dimensions I've chosen. What would it mean if they all had 0 up here? What would that mean? Yeah, it's unit dimension. Independent of dimension. And I gave an example last time, the fraction of this room covered by furniture, right? Commonly, this occurs with fraction. So I could quantify the area, right, of all the furniture here and total it up, measuring it in square feet. And I can measure the area of the entire room and I can divide the first by the second, but the units would cancel, right? Or I could measure it in meters, right? Square meters for all the furniture, and I can measure the whole room in square meters, and I can divide it, but the units would cancel. So that value I get will be the same, right? 0.2 or whatever of the room. And that would mean if we changed our length, how we measure length from meters to feet, it's independent of that. If we changed how we want to measure currency, it'll be independent of that. If we change how we want to measure time, it doesn't care about whether we measure time in centuries or milliseconds, femtoseconds or millennia. It doesn't matter. Or whether we quantify people per 100,000 or per person or what have you. Doesn't matter. These are quantities that are independent of our dimensions. And I use fraction because it's the easily appreciated one. But many of the most profound quantities in physics, chemistry, and indeed in areas when we really think carefully about how a system works, are described in dimensionless way. Because the universe, how the universe runs does not depend on our units. It has to be amenable to description. in a way that is independent of our units. If Canada changes over from imperial to metric units in 1970s or what have you, 80s, you know, that didn't change the rules of the universe. So like suddenly they broke, things like that, right? Rome didn't fall because they started counting, you know, starting to measure time in a different way. The universe operation has to be amenable to description in a way that doesn't depend on unit system. That, in other words, is independent on unit systems. So it's not just that we forget units, it's that it has to be able to be described in a way that is independent. It's not going to change depending on our unit system. This is a profound fact, and it actually really helps us arrive at models that are more rigorous. And one of the key things is it means that we need to describe models in ways that are dimensionally consistent. That's a key factor. We cannot have models which just add things of different dimensions, that add people to dollars, as if that's meaningful to have one person to $2 and say it's 3. That is numerically correct that 1 + 2 is 3. It is meaningless to say 1 person plus $2 gives 3. Like it has no meaning associated with it. The world, models of the world have to be able to be described in ways that don't involve adding together incommensurate things that are measured in different units or different dimensions. So when you're building models, one of the things that constrains how you describe it is you want the formulas like you write for a system dynamics model or for an agent-based model to be dimensionally consistent. You shouldn't be doing things like adding persons to dollars to determine the stress levels of people in a model. You need dimensional conversion constants and so on that will allow you to add things meaningfully that are dimensionless or of the same dimension. And this explains a lot of the forms of formulae you see actually in models. This ability to add things up in a meaningful way, not in a way that is numerically viable but semantically meaningless. Okay, so I introduced in the final minutes of last class, I introduced some notation for indicating the dimension of something. I put down, if I have a quantity, maybe it's S, and a system dynamic stock and flow infectious disease model, I'll write it in brackets to indicate the dimension. So the way to read this is the dimension of susceptibles is person. I'll just, write this down like the dimensions of new infections. Don't worry, I'll be over there in a minute. Is that might be, forgive me, I'm going to write it underneath it because there's this rough and I want to take pictures of it before the end of the class. New infections, if this is a flow between susceptible and infective, what's the unit? And if these are measured in persons, if these are dimensions person, what's the dimension of this? What does the dimension of the flow have to be? Yeah, person per ton. Good. So new infections, if that's the name of that flow, that would be person per ton. Number of people per amount of time. Right? Notice we can assign this without knowing the formula. You don't have to give a formula right now for it to say that is what the dimension. And that actually constrains the possible formula. The ones that are consistent. Okay, now. So I had introduced over there, just what's on the slides here, that if I put this in brackets, this might be persons. And if I had that new infection, so I'll use a different one, recovery flow might be persons per unit time, or persons to the one T to the minus, right? Rather fun. This is a nice addition. I really needed it a couple of weeks ago when I was demonstrating regulatory processes. Okay. Right. So this is a key thing I need everyone to be rock solid on. When you have a dimension for a stock, dimensions for the flows out to it and that stock are dimensions of stock, what? Over time. Thank you. Thank you, Sheena. Okay. And I introduced first order delays last time and talked about formulas and talked about, and this is where these things get useful. If you start thinking about the dimensions here, it gives you no choice as to what, like, if you realize what the formulas for this has to be. If the unit of this is time, if the unit of this is person, if the unit of the flow has to be persons per unit time, then the formula for this cannot be meaningfully population times tau. It has to be population divided by tau. Are people clear about that? Because it's person per unit time. And if you have a dimension for this, a dimension for that, the dimension for the formula, x divided by tau, if the dimension for x is person, if the dimension for tau is time, right? P and T, the dimension for this is what? Person per time. You just divide the dimension, right? $30 minutes remain. Thank you. Yes. Thank you. Okay. So. Okay, this has a lot of beautiful consequences. I want to emphasize that you can readily perform these calculations with dimensions. So if you have, for example, B times C, if you know the dimension of B and you know the dimension of C, the dimension of B times C is just the multiplication of the appropriate dimensions. EJ may want to note the homomorphic character of that, but it's a beautiful homomorphism. Anyway, so we perform these calculations with dimensions. Are you all comfortable? If you had dimensions for each of these things, are you confident you could perform the calculation with those dimensions? If A is in person, B is in person per time, and C is in time, then the multiplication of person and time will be what dimension? If B is in person per unit time and C is in time, this multiplication will be a dimension what? Person. You add it to a person. Is that okay? Yes, it's meaningful. If you added person to time, it would be totally meaningless. Numerically, you could do it, but it would be rubbish. It'd be full of sound and fury, signifying nothing. This is meaningful, adding things to the same dimension. And so we have persons up top now. From adding person to person, we get a person, second of dimension person, divided by something that's dollars. What's the overall dimension then?
Person per dollar.
Person per dollar. Yeah. How many persons we could say per dollar invested in contact things? Okay. Now, okay, there's some really important things here that I'm not going to mention. If we have E to some value, I'll call it V. This has to be dimensionless. It must be that this is of dimension 1, it's of unit dimension. Unit dimension. And that you could see that for those familiar from it, from the Taylor series expansion, you're adding a 1 to b squared over 2 b cubed. And if b is anything but dimensionless, b squared will be different than b in dimension. It'll be like adding a square foot to a linear foot. It would make no sense. It has to be dimensionless. What's in the exponent must be dimensionless, and same thing for a to the b. Okay. Right. Okay. I want to go through some little examples. I'm going to come back to this one, but I'm going to do another one. And I'm doing this now with you because soon I'll do it. You'll be doing it to demonstrate your own. Quizzes will be coming back, and those quizzes will include asking you about dimensions of things. So here's our classic SI model. This is a typographical travesty where this dot should be over the R instead of next to it, but instead of diagonally over it. Please imagine that it's just over it. This is dr dt. This is the rate of change of R per unit time. Rate of change of R. Okay, suppose S, I, and R are persons. The question is, what is the dimension of other quantities? Well, look, we know this entire quantity, what does it have to be? This is the flow out of S. So what does it have to be a dimension? Person per unit time. And here, I just want to walk through really quickly what the dimensions are. Beta is a probability. It's probability of transmission of infection for every contact between a susceptible and infected. If susceptible or infected come into contact, what's the probability the infection gets transmitted? So probability. What's the dimension associated with the probability? I said it last time, but what is it? It's a fraction, so what's the dimension? Yeah, unit dimension. It's a fraction because it's like the fraction, you flip a coin 100 times, what fraction of the coin flips turn up heads? Right? It's a probability. So it's independent of whether you measure the coin flips and per coin flip or per 100 coin flips or per 1,000 coin flips. Whether you quantify that, it cancels. So dimension 1. C is how frequently each person meets another person. It's actually 1 over time. So frequency of connections. How many connections they have per unit. Okay. Mu, the duration of infection is of unit time. What's the dimension of I over S plus I plus R? Unit dimensions, fraction. So let us calculate the dimensions. C is of dimension 1 over time. We multiply it times S. What's C times S? What's the dimension of that? Person per unit time. Times this, you said this is of dimension what? Unit dimension, so 1 per person per unit time, times something of dimension 1, which is this whole thing is of dimension person per unit time, times beta, what's the dimension of that? 1 unit dimension. So the whole thing is of dimension person per unit time. Is that what we want? For S dot? It is. It's what we want. Same thing with this. This is just subtracted from this. Here. This mu is the duration of time they spend infected. So I over mu is of dimension 1. Person per unit time, right? That's what we want. Is subtracting this person per unit time from this person per unit time meaningful? Darn right it is. And this is person per unit time. Okay, okay. Okay, there are more sophisticated models we could go into, but at the end of the day, they're all going to be dimensionally consistent. And we don't have the time to go into these. I want to go instead into one particular one, which I've uploaded indeed onto the site. So I'm going to close this, although we could go vastly further with dimensional analysis.